Three Pythagorean identities. Okay, the first one was Papa Pid, just to help us remember which one's which. Papa Pid was the main one. It's cosine squared of x plus sine squared of x equals 1. Then you got Baby Pid number 1, which is 1 plus tangent squared equaling secant squared of x. And then you got Baby Pid number 2, which is 1 plus cotangent squared equals cosecant squared of x. So if you know Baby Pid number 1, remember you just add cos to the two terms to get the other one. And they're not co-functions of each other. They're not co-ident. You can call them co-identities if you want, but they're not complementary identities. They're baby pids. And we saw why that they're baby pids. Remember asexual reproduction from Papa Pid. Memorize those. Okay. The next two sets of identities you also know as well. There's the even-odd identities. Sine and its reciprocal cosecant are odd functions. So if you ever have a negative on the inside, what do? Bring it out front or forget about it? You bring it out front. Bring it out front. Now, it also works the other way. If you have a negative out front, you want to get rid of it, you could bring it back to the inside. We typically don't do it that way, but it works. So sine and its reciprocal are odd functions. What do we know about these two guys, tangent and cotangent? They're also what? They're also odd. So I just listed them as reciprocal pairs. Tangent and its reciprocal cotangent are odd, so the negatives come out front as well. And then we got the only two that are even, right? Cosine and its reciprocal secant. Those are the only two that are even. So if you ever have a negative input, you don't bring it out front, you just forget about it. Okay? So we now have formally stated those as identities. Okay, the left side is equal to the right side for all values of x. The co-function identities. We have been alluding to these identities from day one when we learned about sine and its co-function cosine. Do you remember what the co stood for? This complementary. Co equals complementary. Okay? And two angles are complementary if they add up to 90 degrees. So, what would be the complement of 30 degrees? What would be the complement of 30 degrees? What'd you say? No? 60. Because two angles are complementary if they add up to 90. So if I give you one angle like 30 degrees, its complement is 90 minus 30, which is 60, right? What would be the complement of 10 degrees? 80 degrees, right? So if you have one angle, the way you find the other angles, you just do 90 minus, right? 90 minus the given angle gives you the complement of that angle. Well, instead of using 90, we're going to be using pi halves. They add up to 90 degrees, which is pi halves radians. So here we go. Sine of x is equal to the complementary function cosine of the complement of the angle x. How do you find the complement of angle x? Pi halves minus x. Okay? It works the other way around too. Cosine of x is equal to its cofunction sine of the complement of x, which is pi halves minus x. So that's how we get pi halves minus x. That's the complement of x. So cofunctions at complementary angles have the same ratio. Here's an example, right? What's sine of 30 degrees? Well, according to this, sine of 30 degrees should equal cosine of what? 60 degrees, okay? Well, that's the same as sine of pi 6, which is 1/2. And this is the same as cosine of pi thirds, which is also 1/2. Do they both equal 1/2? They do, yeah. So complementary functions at complementary angles have the same trig values. That's what we say. All right, the next set of complementary functions are tangent and cotangent. So tangent of x is equal to cotangent of the complement of x, pi halves minus x, and vice versa. And then we've got secant and cosecant. Okay, they're complements of each other, so their trig ratios are equal at complementary angles. So we've been talking about that. We haven't seen them written like this, but we should understand why they're written like that. Let's just make this right here. Pi halves minus x is the complement of x. That's what we call it. Complement of x. Pi halves minus x. All right, so let's talk a little bit about verification, because I mentioned this when we were proving the identities using x, y, and r. In mathematics, there's a huge difference between verifying something and proving something. Outside of a math class, some people might use them interchangeably, right? If you verify that it's raining outside, you go outside and you get wet, right, from the sky, and you're like, yep, I verified it's raining. But is that the same as proving that it's raining? Well, maybe in the real world it's the same thing, right? But in math class, no. If I want to know if it's raining outside, I got to check outside this window. I got to check outside that window. I got to check outside the window next door. I got to check outside all the windows on campus. And then I've only verified that it's raining outside all those windows. That doesn't mean in math that it's actually raining outside everywhere. Okay? So the difference between verification and proof is this. Verification uses finite y values, actual numbers, and it only proves that it's true for those numbers. Like right up here, we just verified this. We have verified for x equals 30 degrees. Okay? That's it. If I use 30 degrees and its complement 60 degrees, I've only proved that it works for these values only. That doesn't mean it works for all the other angles. Proof is showing that it's true for all cases, and the way that we do that is we use variables. Okay, as we already saw up above when we proved the Pythagorean identities. We use variables. Okay, here's the important thing to get across. No amount of verification constitutes a mathematical proof. I can verify that these identities right here are true for a gazillion numbers. I can create a list of angles that I've tried out over the course of my lifetime, and it numbers into a gazillion. Is that even a number? I don't even know, but it's a huge number. That doesn't prove that these work for all angles. It only proves that it works for those specific gazillion numbers that I've tried it out. Okay? No amount of verification constitutes a mathematical proof. So let's try example 4. For both pi 6 and 7 pi fourths, verify that tangent is equal to cotangent of the complement of x. Okay, so here's how we verify. We write tangent of pi 6 on one side, and we put cotangent of pi halves minus pi 6 on the other side. And just like we do with the proof, we draw a line down the middle, but notice we're not proving, we're just verifying because I have specific values there. So what is tangent of pi 6? You all remember from our unit circle days? I evaluate the left side. Square root of 3 over what? 3. Very good. Tangent of pi 6 is square root of 3 over 3. Hey, what's the inverse tangent of square root of 3 over 3? Or the arctangent of square root of 3 over 3? Pi 6. Very good. Now on the right side, I got to find the common denominator. So pi halves is the same as 3 pi 6 minus 1 pi 6. That gives me cotangent of 2 pi 6, which is the same thing as cotangent of 2 pi 6. That's the same as cotangent of pi thirds. What's cotangent of pi thirds? Square root of 3 over 3. Are they the same? Yeah. So we don't write booyah or dirty diapers at the end because we're not really celebrating it to the same extent that we would if it were proof. So we just put a check, which means, yeah, it works. Yeah. So I know that this identity, it works for pi 6. And that's it. That's all this tells me, that it works for pi 6. Does it work for 7 pi fourths? I don't know. Let's see. Tangent of 7 pi fourths on this side equals cotangent of pi halves minus 7 pi fourths. We'll draw a line down the middle. What is tangent of 7 pi fourths? No. It's quadrant 4. The ordered pair is square root of 2 halves, comma, negative square root of 2 halves. Negative 1. The y values are the same magnitude. The x and y values are the same magnitude on the unit circle, but they're opposite signs, so it's negative 1. All right, now over here I got to get a common denominator, so that's the same as 2 pi fourths minus 7 pi fourths. 2 minus 7 is negative 5, so I get negative 5 pi fourths. Negative 5 pi fourths is coterminal with what? Within one positive rotation. Negative 5 pi fourths is over here, right? It's coterminal with 3 pi fourths. So remember, one of the theorems we had is that coterminal angles have the same trig values. So if I say cotangent of negative 5 pi fourths, even though negative 5 pi fourths and 3 pi fourths are not equal angles, they have the same cotangent value. And what's the value of cotangent over there? It's also -1. Does -1 equal -1? Yeah. So do you trust this identity now to work every time? After we verified it only twice for only two angles, do you trust it to work every time? I wouldn't, not after two tries. Now, I told you up here that it is an identity. So if you take me at my word and you trust me that it is in fact an identity, then you can say, I have a feeling it works for all values in the domain. And you're right, it does. But we haven't proven that yet. And we can't prove this yet until we learn some other identities called the composite identities. We don't have enough uh, we don't have enough tools in our tool bag yet to prove this. We can only verify it.
What happens if they aren't able to verify it? Do you just put like DNE or?
No, if they don't equal each other, we put this. You remember what this was? That means contradiction. It's like two ramming arrows saying, I don't think so. Not on my watch. Okay, that's if they're not true. Now, I'm glad you brought that up because if I plug a number into the left side and the right side and it's not the same at the bottom, congratulations, you have just found a counterexample. What does counterexample mean in this case? It's not like a display of a countertop, right? Here's a counterexample. Yeah, a counterexample, like if you say, hey, it's raining outside, I could provide a counterexample by saying, not outside my window. There's no rain falling right now. And you're like, well, yeah, but what about other windows? Well, maybe so, but not outside my window. That's a counterexample. If I said that x equals 1 for every value of x, is that true? Does x equal 1 for every value of x? No. Can you give me a counterexample? X equals 2. Very good. Because 2 doesn't equal 1. 2 is a counterexample. So is that an identity right there? X equals 1, is that an identity? It can't be an identity because identity has to be true for all x. It's a conditional equation. It's only true when x is 1. Okay? So that's a counterexample. Now, very often it's much easier to disprove something than it is to prove it. Okay? Because it only takes one example to disprove something. That's it. Remember I told you earlier if I would have had a gazillion values that worked, I can't say it works for all values of x because there could be that one value that I still haven't stumbled across that when you try it out doesn't work. And for mathematics to say something is true for all values of x, it has to be true for all values of x. Okay? Every single one of them. Even if it's true for a billion things but not just one, then we say it's not true. Okay? A counterexample. Let's find some counterexample to disprove the following quote unquote identities. You know what it means when we have identities in quotations? It means that it's not really an identity, right? It's a fake identity. These are some things that students try over the years. Is it true that the square root of x squared plus y squared equals x plus y? Is that true? No. Have any of y'all here ever tried to do that? I hope not. There was a student in BC Calculus this morning that had this. We were working a problem and it was this, 4x squared plus 4x to the fourth. This is what we were working with. And he literally asked me this morning after the review, is that the same as this? He literally asked me this literally this morning. Is that true? What do y'all think? Can we do that? No, that just means that we're finding area under a curve. That's all that means. But the algebra was this. He wanted to know if this piece right here was equal to this piece right there. In other words, if you have multiple terms under a radical, can you just take the square root of each term? And of course, y'all know the answer to that is what? No, no. And he was a BC calculus student. He still thought that it actually worked. That doesn't work, okay? That's what we're saying right here. The square root of x squared plus y squared does not equal x plus y. Now, if we try to find a counterexample, let's try some out. Let's let x equal 0 and y equal 1. Let's try it out. Okay, I'm going to get the square root of 0 squared plus 1 squared. Does that equal 0 plus 1? We'll try it out. What's 0 squared plus 1 squared? Well, that's 0 plus 1. That's the square root of 1, which is 1. And over here we get 1. Hey, does 1 equal 1? Yes, it must be true, huh? Guess what happens if you're trying to find a counterexample and you find an example that actually works? What do? You keep searching, right? Because this is not an identity. Now, that doesn't mean that it might not work for some values. This actually works for several values. It works when x and y are both 0, and it works when x and y are either one of them is a 1 and the other one is 0. So that doesn't work. We got to keep searching, okay? Let's pick some values like x equals 3 and y equals 4. Let's try that. So does the square root of 3 squared plus 4 squared, does that equal 3 plus 4? Well, let's try it out. 3 squared plus 4 squared, that's 9 plus 16 under the radical. That's the square root of 25. What's the square root of 25? 5. And on the right side, what's 3 plus 4? 7. Is that a true statement? 5 equals 7? No. So we put the little contradiction arrows there, which means not true. Now, because we found one thing that disproved it as an identity, guess what? We now say that it's not an identity. We put the not equal sign there, and we never try that again, right? Even if we're in BC and we're desperate, we never try that again. It will not work. Even though it works sometimes, it has to work all the time, and we just found something that showed it doesn't work all the time. Got it? Okay. Don't ever try that again. Another famous one that students like to do is this. It's kind of the same idea. X plus y squared, is that equal to x squared plus y squared? That is also not true. Also not true. But people want to think it's an identity, and it doesn't work. Okay. Now here's one that's trig related. Sine of the quantity x plus y. Do you think that's equal to sine of x plus sine of y? In other words, can we distribute the sine inside of its own angle? When we get to things like this later on in the next section, you're going to have the urge to want to do that. You're going to want to say, oh, sine of x plus y. That's sine of x plus sine of y. But you know what? It's not an identity. Let's see why. Let's pick some angles. How about, let's pick, what do you want to pick for angles? Let's set x equal pi 6. And we'll let y equal pi halves. Let's do that. So on this side, we get sine of pi 6 plus pi halves. And I want to know, is that equal to sine of pi 6 plus sine of pi halves? All right, so on the left side, I got to get a common denominator, which is 3. So that's 4 pi 6. That's sine of 2 pi thirds. And sine of 2 pi thirds is square root of 3 over 2. On the right-hand side, sine of pi 6 is a half. And sine of pi halves is 1. So I get 3 halves. Does 3 over 2 equal the square root of 3 over 2? Nope, it doesn't. Now, are there angles that actually work on both sides? Sure, yeah. If you let x and y both be 0, you're going to get 0 equals 0. So that's why you want to choose values that are non-typical. Like, don't choose some of the quadrantal angles. Mix it up with some of the interior angles. So this never works, okay? This will never work, and it doesn't work with any of the trig functions. You cannot distribute a trig function inside to its own angle. You got it? We just disproved it. Don't ever try it.
Is it sine of x times y, sine of x plus sine of y?
No.
What was that?
That was the log. You're thinking of logs. The natural log of x times y is the natural log of x plus the natural log of y. But it doesn't work for sine. Sine of x times y is also not equal to sine of x plus sine of y. Now, you're lucky. Sine of x plus y is going to equal something, but it's not sine of x plus sine of y. You cannot distribute something inside of its own angle. So don't ever try it. I bet there's going to be at least one or two of y'all in here that'll still try that later on because you're going to be desperate and you don't know what to do. You're going to try to distribute it, and it's going to be RONG, which is wrong. That's the wrong way to spell wrong. All right, how about this one? Cosine x plus sine of x equals 1, right? Is that Papa Pid? What do you mean it's not Papa Pid? Oh, they got to be squared. Oh. Well, what if they were both squared? Couldn't I just take the square root of both sides? And the square root of 1 is 1, and the square root of cosine squared is cosine, and the square root of sine is sine. Does that work? Can I just take the square root of both terms? No, we just proved that over here on part A, didn't we? It doesn't work with x and y. It doesn't work with cosine and sine. So you're right. This is not true. This is not true. In order to be Papa Pid, the angles have to be squared. This is not squared. Let's pick an angle. Let's pick an angle like pi 6. Watch, I'll show you. Cosine of pi 6 plus sine of pi 6. We'll draw a line down the middle. That's going to be square root of 3 halves plus 1 half, which is the square root of 3 plus 1 over 2. Does that equal 1? No, they have to be squared. They have to be squared. Okay, now we're getting into the fun part. This is going to give you a taste of proofs. Simplify the following trig expressions down to a power of a single trig function. So I want it to be trig to some power of n of x. It could be sine to the first, it could be cosine to the fifth. I want to simplify it down to a single power of a single trig function. Okay, so we have this vague target. Let's look over here on part A. What can I do when I'm simplifying? Well, here are the rules. I can combine like terms. I can divide out common factors. I can expand an expression, like FOIL it out. I can factor an expression. What else can I do? Oh, I know what else I can do. I can replace a trig expression with one of its identities. I can replace something with something that it's always equal to. That's what identities are good for. They are mathematical substitutes for something else, synonyms. All right, so let me look at this with y'all. And what do y'all notice? Is there anything that I can do right away? Yeah, I could call sine cubed of x. I could call 1 over cosecant cubed of x. That would work, right? That's using the reciprocal identity. Yes, yes? Okay. What could I do in the second one? Could I leave the sine in the top and bring the cosine squared to the bottom and say it's secant squared in the bottom? Does that work?
Well,
It actually does, right? Because cosine squared is 1 over secant squared. So yeah, if you put this over 1, you could bring anything from the top to the bottom and the bottom to the top. In fact, if I wanted to do this, look what else I could do. If I wanted to leave the cosine squared in the top, I could bring the sine to the bottom and call it cosecant of x. Like that. That also works. Yes, yes? So we haven't done anything wrong on either one of those. But here's the question. You start having these options. You have all of these things that are possible. And you know they're possible because you have memorized the identities. But our goal is to simplify it down to a single term, to a single power of a single trig function. So my question is, are either of these things that we've done here that are not illegal, does it make sense to do them to establish our goal? Not really. Not really. Just because something's possible doesn't mean that it's the route you want to take in that particular moment, right? So I'm going to abandon both of these ideas, and maybe I'll come back to them. Let me shrink it down. Maybe I'll come back to them. Here's what I'm going to do. I don't want to necessarily complicate it and put it in terms of sine and cosine. What I'm noticing right away is I have a common factor of sine in both of those. Do you see that? What can I do if I have a common factor? I can divide it out, which means factor it out. I'll pull it out front. What am I left with on the inside in the first term when I factor a sine of x out of a sine cubed of x? I'm left with sine squared of x. Yes, yes. Plus, what am I left with in the second term when I factor out the only sine that was there? I'm left with cosine squared. So that's what we're doing there. We're factoring. Now that I factor, I have it as one term, which is what I wanted. So now I kind of retake inventory. And I'm noticing on the inside now that I have sine squared plus cosine squared. Hey, if you have your identities memorized, then Papa Pid is standing there slapping you in the face, and you're like, I see you, Papa Pid, I see you. But if you don't know your identities, Papa Pid is slapping you in the face, and you're like, stop that, Papa Pid, stop that, whoever you are. I'm trying to do this problem. Quit slapping me in the face. It's equal to 1, isn't it? So that becomes sine of x times 1. And what's anything times 1? Itself. And that simplifies all the way down to sine to the first of x. Does that meet our goal? Is that a single power of a single trig function? It is. Wow. So this entire expression right here is equal to sine of x. We have just created another identity. This is another identity. Do you want to memorize this identity? No, don't memorize this identity. If you memorize the fundamental identities, you don't need to memorize this identity because it comes from a little bit of algebra and knowing the basic fundamentals identities from which others can be built. You don't have to memorize every identity that comes along. But it is equal to sine. Now, is that the only way to get it down to sine? Absolutely not. If you wanted to continue with this route right here, the second line, that would actually work. In order to combine two terms, you need to get yourself a common denominator, so you can actually multiply the second one by cosecant squared over cosecant squared, and it'll end up working out the same way. It's just going to take a lot longer. Sometimes you take a little more of a scenic approach. All right, letter B. Secant of x minus 1 times secant of x plus 1. I'm trying to simplify this down to a single power of a single trig function. Anybody see anything that we could do? That is a difference of squares. These are both conjugates of each other, right? So you want to recognize that. Something plus 1 and something minus 1 are conjugates. What happens when you multiply two conjugates together? As Peyton said, you get a difference of squares. So in the previous one, I factored it. On this one, I could do this. This could be my first move. I can call secant 1 over cosine. Okay, that's a legal move. Is that going to be helpful? Probably not. Okay, but because I noticed they're conjugates, maybe I'll expand it out. Let's FOIL it out. I get secant times secant and secant squared, and then I get plus secant of 1 of x, minus, on the inside, I get minus secant of x, and on the outside, I get minus 1. That's just expanding it, multiplying it out. What happens with these two secants on the inside? They cancel, and I'm left with secant squared minus 1. Now, what's secant squared minus 1 equal to? Well, do I know what secant squared is? I could call it 1 over cosine squared if I want, but isn't there a baby PID that has secant squared in it? Isn't secant squared 1 plus tangent squared? So can I make that replacement? Can I replace secant squared with 1 plus tangent squared? Yeah, I get 1 plus tangent squared minus 1, and then my 1's cancel, and I'm left with tangent squared of x. Did it work? That's a single power of a single trig function. Now, yes, here's what's cool. If you memorize 1 plus tangent squared of x equals secant squared of x, now that we know it's an identity, you can use it in other forms. In other words, if you bring the 1 across, you can also say tangent squared of x is secant squared of x minus 1. So you could have gone straight from this line to this line without doing the middleman line. That's fine. If you know secant squared minus 1 straight up is tangent squared, you don't have to show me that middle line. But if you know that secant squared is 1 plus tangent squared, it works out to be the exact same thing because the 1's cancel. You got it? All right. Oh, crap. Look at this guy. Bully. What's the first thing you might notice here? 1 over cosine of theta. We haven't worked with fractions at all so far on these simplifying ones. In fact, when we turned them into fractions, it looked like it was going in the wrong direction. So is there anything I could do in the first one to get rid of the fraction? What's 1 over cosine also called? That's secant. So I can call that secant theta minus 1. Very similar to the previous one, right? Now let's look at the second one. I have a 1 over cosecant squared at the very end. What's 1 over cosecant squared? What's sine squared, right? And then I got a cosine squared right here. And now I just got this middle term. It has a different angle. It has a negative angle. How do I get rid of the negative angle to turn them into so that they're all positive angles? I use the even odd identities, right? Is secant even or odd? Do I bring it out front or forget about it? I forget about it. Secant and cosine are the only two where you can forget about it. So that just becomes secant of theta. So that's all I did on the first step. I wrote the two fractions with using the reciprocal identity, and I used the even-odd identity on that middle term in the second factor. Now I reassess. I don't think there's much to do yet in the first one, so I'm just going to call it secant theta minus 1. But what do you notice in the second factor? Cosine squared plus sine squared. They don't have to be written side by side, do they? The associative property of addition allows us to associate them however we want. So I can replace both of those with what? The number 1, and I get 1 plus secant of theta. Oh my gosh, now what have I turned it into? I've kind of turned it into part B, haven't I? If I call that secant of theta minus 1 times secant of theta plus 1, if I commute those two terms, when I distribute, I get secant squared of theta minus 1, which is tangent squared of theta. So those two actually ended up going down the same road at the very end. In fact, this thing right here on the left is an identity to this thing on the right. They're exactly the same. They both equal tangent squared of theta. Do you see what trig proofs are going to encompass? We're going to have to get from one expression to another expression by doing just a combination of algebraic skills, factoring, multiplying, combining like terms, and or replacing things with what they're equal to using trig identities. And it's just the combination of those two things, chipping away at it line by line, that's going to get us to our answer. All right, let's see if y'all can do one by yourself here. 1 minus sine squared over cosecant squared minus 1. Chip away at it. See what you could do here. I'll give you a minute or two. Maybe this is the last one we do today. You have limited experience so far, so maybe you're kind of stuck right away. Here's one thing that you might want to do. Can we divide out these ones? Heck no, because A plus B over A plus C is not B over C, is it? You can only divide out common what? Factors, not terms. So you can't do that. Now, look at the PIDs that I wrote up there. The top line, the top row all the way across, that's as we learned them. But because they're identities, we can algebraically manipulate them. And if you get used to these other versions of the identities, you're going to help yourself. So on Papa PID, if I subtract the sine squared from both sides or the cosine squared from both sides, I get the two other versions that show up a lot. 1 minus sine squared is cosine squared, and similarly 1 minus cosine squared is sine squared. Those different versions show up a lot. 1 minus sine squared is cosine squared, 1 minus cosine squared is sine squared. So what can I call 1 minus sine squared in the numerator? I can call it just cosine squared. Yeah. Now look at the middle identity. 1 plus tangent squared is secant squared. We already saw this on the previous example. If I subtract 1 to the other side, I get secant squared minus 1 is tangent. That shows up a lot. Secant squared minus 1 is tangent squared. Now you can do the exact same thing for the other one. If you subtract 1 from both sides, you get cosecant squared minus 1 is cotangent squared. It's just another version of the PID, and it saves a little bit of time. So what can I call the denominator here? Cosecant squared x minus 1 is what? Cotangent squared of x. So now at least I've got it down to a single trig function over single trig function. Now, can I do this? Do the c's divide out? Do the o's divide out? Do the squareds divide out? Do the x's divide out? Am I left with s over t? Does that work? No, sillies.
You gotta put the cotangent. So what I did was I did cosine of x over sine of x.
Very good. That's what you want to do here. When you get something that is not in terms of sine and cosine, you're going to learn this later on. We can express every single one of the 6 trig functions in terms of sine and cosine. That's how we were evaluating them using the unit circle, right? So if you ever get stuck, you could put all in terms of sine and cosine. So the top is staying a cosine squared, but let's draw the big line. Cotangent squared is cosine squared over sine squared. Yes, yes, using the ratio identity. Are y'all okay with that? I made the substitution. Cotangent squared is cosine squared over sine squared. I put it in terms of sine and cosine. Now, when I do that, I created a complex fraction. And when you create a complex fraction, you should rejoice. You know why? Because the very next step is always to get rid of the complex fraction, algebraically. And the way we could do that here is stay, change, flip. So the top stays cosine squared. The division turns to multiplication, and I multiply by the reciprocal, which is sine squared of x all over cosine squared of x. And then I can put this cosine squared over 1. Now what happens from high to low with your cosine squares? These divide out, and you're left with just sine squared of x. Yeah, there you go. So that's an identity. That original expression up there is just sine squared of x in disguise. Do you want to memorize this identity up here so that if you ever see the left side, you know it's equal to the right side? You want to memorize that? Nope. I'm not going to memorize that because if I need to prove it or I need to use it, I could just prove it using the basic set of fundamental identities that I've already memorized. Okay? We don't put everything back in terms of x, y, and r anymore. What we do is we use the new identities that are in terms of the trig functions to prove other things. So get on board with this right away because when we get to proofs, I don't want you to be left behind. We're just doing algebra and substitutions. Algebra, substitutions. Any combination of those. Substitute, substitute, algebra, algebra. Maybe it's algebra, algebra, substitute, algebra. Maybe it's substitute, algebra, substitute, algebra. You don't know. It's just a combination of those two things. But you got to be fearless, and you got to go inch by inch. It's a cinch. And now we have kind of a strategy, 2 strategies in one. Put everything in terms of sine and cosine if you ever get stuck. And if you get a complex fraction, stay, change, flip. Okay? We'll stop right there. There's 5 minutes left. I don't want to get too far into here. I want some of this to sink in. It looks like we got about 2 more days on this. So we'll finish this Wednesday. It looks like the worksheet's going to be due on Thursday. Okay? Any questions? 6D. We accomplished some things today. 6D. 4 to 6D.